perhaps in one video or not. First, a simulation that will help you see and understand what is happening so you can get a feel for the concept. Second, several worked examples so you can see how to approach pencil and paper problems that you need to master to succeed on your assignments and tests. I hope you enjoy these presentations. If you find them helpful and you want to say thanks, then please go to youcanlearnthis.com and buy me a coffee. Thanks very much. Welcome to this simulation of the law of universal gravitation, Newton's amazing insight and discovery. So what we're going to look at is we have a large planet, or a large-ish chunk of rock, and according to the fine print it has a radius of 850 kilometers, and then we have this smallish chunk of rock and it has a radius of 50 kilometers, so a very small moon with a very, very small satellite. Actually, it's not a satellite because we're just going to be looking at the gravitational interaction between these two, but I'm calling it a satellite, and its mass is multiples of 1,000 kilograms, whereas the planet's mass is multiples of 10 to the 20th kilograms, so overwhelmingly more massive compared to this. And that's so we don't have to worry about the motion or acceleration of the large planet. In effect, it's zero compared to this. So as you probably know, there's a force of interaction between these two masses, as there is between every two masses in the universe. And you probably already know Newton's formula describing the magnitude of that force. That's the one with the big G, the two M's in the numerator, and the R squared in the denominator. And that R is a little confusing, it can be. We tend to think of R usually for radius, but that R in that formula is the distance between the two masses. Indeed, it's the distance from the center of the two masses, center to center distance. And that's why on the graph I have the x-axis denoted with an R, and C to C, center, center, and the scale on the x-axis here is in kilometers, although when you actually use that formula you have to do everything in meters. So there's always a bit of unit conversion going on with these situations. All right, so what we're going to do is I'm just going to play with the different masses at different distances, and we're just going to look at how the force of gravity varies in that situation, and we're going to watch the blue mass move toward the gray mass, and we'll see a graph of how the force of gravity changes, because of course as it gets closer the force becomes stronger. So let's see how this works. So what do we got? We've got a mass of the blue guy of 12,000, and the planet starts out at 5 times 10 to the 20th kilograms, huge numbers, and the satellite is that 20,000 kilometers is the center to center distance between them, not from the blue mass to the surface, but from the center of the blue mass to the center of the planet. And when you're using that force law, you always have center to center distances. All right, let's run it and see what goes on. So, clunk. Oh, we even got a clunk sound. Maybe you didn't hear that. Let's back up a bit. All right. Now, we'll look at this first, and then we'll look at the graph. So what's happening is that the planet is pulling the satellite with a certain force, and that vector represents the magnitude and the direction of the force of gravity acting on the blue mass. But it's a mutual thing. So the blue mass is pulling the planet with a force pulling it toward it, and the magnitude of these forces are identical. So when you use that formula, you are computing the magnitude of these forces, and it is your job to recognize that those forces are acting upon both the masses, and they are acting in such a way that they attract each other. So it's easy to forget, because of the kinds of problems we do, that the satellite, the small mass, is exerting a force on the planet. And the reason it's easy to forget is that the magnitude of the force of gravity when acting on the blue mass is large enough to accelerate it in a measurable way. But the magnitude of the force of gravity acting on the planet, even though it's the same magnitude as this, because this planet is so massive, the acceleration is virtually zero. I mean, just think about F equals ma. Well, if m is enormous, then a is going to be very, very tiny, virtually zero. So don't forget about this force here, although it's easy to do. if we go over to the graph now, what it's showing us is what is that force of gravity, the magnitude of this, the magnitude of those vectors, just one of them. They're acting on different masses. That's why there's two of them shown in the diagram. And it's basically showing us that at the beginning, when they were 2,000 kilometers apart, center to center, 2,000 kilometers, the magnitude of the force was about 100 newtons. Okay, so that's there. But as time, it looks like we're going in increments of 0.2 of an hour. As time marches on, the blue satellite falls, quote unquote, and so the center to center separation decreases, and so we're going from 2,000 to, well, we don't quite hit 1,000, but almost 1,000. So that distance is 1,000 right there. And now the force of gravity is nearly 350. So that's why it's that. And we can see that it's not a straight line. And if you think about the formula, we're plotting the force of gravity versus the separation r. So it's basically the force is like the y coordinate, and if you ignore the numerator g, m, and m, because they're constants, so you can just pretend it's a 1. So this is the graph of 1 over r squared, and you may know from math that 1 over r squared has this shape in the first quadrant. So that's why we have this kind of curve, and the function is, to speak mathematically for a moment, the function is decreasing in the sense that as the separation increases, the magnitude of the force of gravity decreases. The farther apart they are, the smaller the force of gravity. That force is never going to go to 0, okay, because r squared will always be something. Even if it's huge, it's still a large number, and it will mean that the force of gravity will be positive. So everything in the universe, no matter how far apart, is pulling on everything else in the universe. But there are other issues involved, so that to explain why everything in the universe isn't just rushing toward each other, because they're all pulling together. All right, so that gives us a basic idea. Now all I'm going to do is I'm just going to quickly change some of these values, and you'll just see how that affects the shape of the graph, just to give you a feel of what things look like. So here all I've done is I've cleared everything off and doubled the mass of the planet. So now it's 10 times 10 to the 20th kilograms. Satellite starts the same displacement, center to center is 2,000 kilometers. So when we run it this time, all right, we're ticking away here. Okay, we got the collision right about there. Now, the forces are now much larger, and that makes sense because the formula has got the two masses in the numerator. So if the mass of the planet is doubled, then the force of gravity will be doubled. And when we work out the problems, you'll just see that that's the case. And that makes the graph steeper because the force is larger at any given distance. The force is twice as much. This is what it looked like before. But now that force is doubled, so it's just steeper. And again, the planet pulls the blue mass with this magnitude of force, which here is 613 newtons, and the blue mass pulls the planet with that much force. So these forces, though, don't cancel because they're acting on different masses. So this force accelerates this guy, and this force accelerates this guy, but the acceleration here is so small we can ignore it. All right, so let's just run that one more time. I don't think it'll be any surprise if I change that to a 15, and okay, here we go. Clunk. All right. And now the magnitude is even bigger. Should be 3 times what it was originally because the planet has 3 times the mass. Now the scale here has changed and the numbers have gone kooky, so I'm going to do some resetting and see if I can fix that, but nothing too surprising there. Well, this time let's make the satellite, let's shrink it. Let's take it down to 6,000 kilograms and see what happens. All right, same thing. We still have attraction, but it's less. Oh, I should have taken the, let me reset this again. I should have taken this back to its original. There we go. So it's as when we started, except now I made the satellite's mass half of what it was. And of course that decreases the force of gravity. All right, so if we stop things, okay, so we have much tinier force now, and you can see that that's reflected here. Force of gravity is just less. There it is. And let's just play with our initial starting position. So what I'll do is let's take this back to say 12, leave that at 5, but let's let the satellite start at 3,000 kilometers. See what goes on. Ooh, okay. Well, at 3,000 kilometers, the force is considerably weaker, and so it starts out very low indeed. But eventually, the closer we get, the stronger the force, the greater the acceleration, and therefore the greater the velocity. You'll notice we're not talking about those things at the moment. We're just appreciating how the gravitational law works. So if we start far away, r is larger, r squared, which is in the denominator, is larger still. And so that makes the force very, very small. And so it takes quite a while for anything to happen. As you can see, the time is much longer. You won't have to calculate stuff like that in a high school course, at least, that's for sure. Okay, let's just do a quick change to, let's start it much closer, 500. Ooh, now that's interesting. You see, I put 500 because that puts it right inside. So that was a silly number. Let's say 1,000. There we go. Because remember, this number is the center to center distance. I forgot that. Well, 1,000, that's too close to even get started. Let's make it 1,500. All right, let's run it. Okay. Well, no surprises, I should think. It just starts closer, and there we go. Now, you may be wondering, why haven't we used Newton's universal gravitational law when we were messing around with the force of gravity of objects just a few meters above the ground? So let's say we were just a couple of meters here, and then we threw things up, and so it was further away. So the force of gravity would actually be less as we throw a ball in the air. It gets further away from the center of the Earth. So the force of gravity is less, and then it comes back, force of gravity is more. So the force of gravity is changing when we throw balls in the air. But as you've probably intuited, that change is very, very tiny if we're just dealing with even a few kilometers. So we can just assume that when we're near the surface of the Earth, and near, in my definition, is between us and where the airplanes roam. If we're near the surface of the Earth, the force of gravity is essentially a constant, even though we could, if we wanted to, we could compute the difference. But we never do that when we're solving those early kinematics problems. All right, that gives you a look at how Newton's universal gravitational law works and what you can expect from a graph. I'm going to say one more thing about the graph. Let me just, oh, it keeps complaining, isn't it? So let's reset everything, and I want to change that to, say, 3,000. And let's make this a bit more massive and run it. I just want to get it curved. So this is just a heads up. This is not something you're going to do when you first learn about the force law, the universal gravitational law. Okay. But I do want to show you something. Way back at the beginning of the course, when you looked at kinematics and you were looking at the diagrams, and we had distance versus time and velocity versus time and things like that. Well, here we have force versus a distance, the separation. And it turns out that the area underneath this curve has meaning. And that area is telling you the change in the potential energy of the satellite. So even if you're not quite sure what potential energy is all about, when the satellite is way up here, it's got a long way to fall, so it can gain a lot of speed, and so it can gain a lot of kinetic energy. So we say that it has a lot of potential energy, as if there were a spring between the planet and the mass, and that to get it out here, we pulled it away and we were stretching that spring. So there's the energy stored in that spring is the potential it has to turn into kinetic energy as it falls down. Anyway, it turns out to be a useful thing to be able to compute that potential energy, and that's represented by the area underneath this curve. And it has a nice formula that's not intuitive unless you've taken a first course in calculus. So just to give you a heads up that watch that area, think about it a little bit, because it will occur later in your physics course. Well, thank you for watching, and if you want to find the follow-up video of this, which will show you how to do some typical textbook problems, then please go to youcanlearnthis.com and you will find stuff there. Thanks again.